that you'd understand at the end of the lecture, concepts of regression and the types of regressions, learn how to fit linear and logistic regressions, and I think there'll be, possibly we might do a few other regressions, and then visualize and interpret regression results. There are obviously some really nice references that you could use, some of which I've used partly for these notes. One specific one, the epidemiologist R handbook, is easy. It doesn't have too much, has the main concepts, you could look into that, and there are obviously other numerous resources online, books and websites that can help you improve your skills under regression. Why regressions? I think from the very first day we talked about relationships between outcomes and explanatory variables. And that's like the core of epidemiology. We are interested in knowing the relationships between, say, survival or death or sickness or good health, and what would explain those two events. And if you identify explanatory variables that explain a lot of what you're observing as the outcome, then those are possible to manipulate and improve the health of the population. That's the whole idea. Now, regression analysis are really a statistical tools. They are basically statistical tools that you use to help you make the connection between outcomes and explanatory variables. And the regression models can be used for many things. One of it is just to understand how outcome variables change. You change, say, the explanatory variable. It helps control for things like confounding. Remember, we were speaking about like cause and effect, and you know sometimes the example of down and rank. You know that the most important. I think I might have to drop this. It's yeah. The relationship between the risk of Down syndrome and birth rank is not necessarily that the birth rank is responsible for it, it's more the age of the mother. So with the regressions, you are able to account for the age of the mother and then see does really birth rank link with Down syndrome. And I think the most, one of the most critical parts of using regressions is making some predictions. So how much of the outcome variable might change based on values that you change of the explanatory variable. So take the example, if I am a farmer, I'm interested in selecting animals at birth to determine which one I should have later. So if, for instance, the weight at birth is a really good predictor of weight at 1 year, and I want to sell my animals at 1 year, then if I was to select, I would want to select animals with the best weight at birth. Now, for me to make that decision that weight at birth is related to weight at 1 year, then regressions become important. And if I have a really good relationship, I can use that as the determinant very early on when animals are born for my decisions as to which animals I'll keep and which ones I'll not keep. So that kind of is an example of how we might use predictions of outcome variables based on, say, birth weight as an explanatory variable. So what in a really simple sense is regression? It's this statistical method that we model the relationships between variables, and we have one variable that would refer to as the dependent variable. The one that changes is dependent on, and then you have got the independent variables, which you hope to manipulate as an epidemiologist or as a public health specialist to get your desired results. So basically then they'll help us understand what's the value of the dependent variable as it changes dependent on the independent variables. So there are two types of regressions we'll focus on this morning. The first is the linear regression, and the second one is the logistic regressions. Very quickly, but there are numerous other regressions, and I'll give you at the end of the lecture like many others that you should think of. So for linear regressions here, we are interested with basically when the outcome is continuous. And I think you have been given these examples lots of times. When I look at all of you standing, like when you're taking the photograph, there are people who are told, please move to the front. Others are told, please move to the back, because your heights are varied. You have a continuous, variable of heights in this class. And then there is obviously the logistic regressions, which deals mainly with variables that are binary. You pronounce yourself male, then that's one, and female. Or you're alive, I can assure you in 100 years, all of you will be dead. Like life and death. Like those are two binaries, right? So the simplified process of running a regression, the initial thing, for the outcome of interest, you need to know what its distribution. Essentially, we want to describe if it's, say, the heights of people, you'd expect that the heights of people would be, most of us will fall in a certain range, and there will be very short people, and there will be possibly very tall people. And what you're getting there is almost a uniform distribution. So by distribution, often you're referring to this set of objects that are not identified individually. So e.g. heights of a set of unnamed individuals, like this class. If I take your heights, that's an example of, and then I plot those heights, that's an example of a distribution. And then you can observe how does your distribution look like. In statistical modeling, we want to assume the data is generated from a specified probability distribution. So heights is a normal distribution, and yes, no is what kind of distribution? I think you have been talking about this quite a lot in the class. So then we fit a distribution to the data of outcome, which we refer to as y, and then we get these predictors, x, which could be, can that be determined by you being male or female? That's an example of a predictor, or it could be based on the height of your mother, or the height of your father, or the kind of food that you ate. So that x is potential explanatory variables for why you are as tall as you are now. And so we model your current height dependent on those predictors, and we know that there's some error as well in terms of measurements and all. Then we estimate parameters of the model to say, for instance, if you're male, you're on average 2 centimeters taller than a female. Then we can use that to make a prediction that a child is born. It's actually around Christmas. So a child is born, and we know their height, and we can make a prediction. If they have 6 months of breastfeeding, and they have got good weaning, and they have got good access to vaccines, then we expect their growth to take this kind of trajectory. So we can make a prediction, what if we vaccinated our children, or we gave them milk, or we ensure they got enough water, what you do expect in a population to observe. Then you have to evaluate that model to determine whether it's a good fit for your data. Is it a good, can you depend on that model? And then there are ways of evaluating that. And based on that, you can make your decisions. So it's a simple way of taking a complex world and finding the most important characteristics of that complex world and seeing whether those characteristics, if well understood, can help you make decisions about the future or what to do right now. And George mentioned to me this morning, he has talked a lot about this kind of different distributions. In a sense, there are two main types of distributions, like the discrete distributions, when you use that when the data can only take a finite number of values. So like how many children can a mother give birth to, or the number of cars within a parking lot, or even how many heads and tails if you toast. Okay, so then there's continuous distribution when the data can take any value within a range, whether it's heights of individuals, weights of babies, it could be even amount of income. I suspect you all earn very different amounts of monies. And in the context of the programming language you've been using here, then there are specific functions that help you get that distribution if that's what you need to work with. I found this newspaper article from not too long ago about the heights of Kenyan men. It's a paper written in 2016. It has huge messages. The first message is that a man of 1962, just before independence, was taller than the current man, on average. Do you agree with it? When did you get your adult height? At what age? I'm talking about you, not anybody else. When did you get your adult height? Huh? At 15? Uh-huh. Boru? You don't remember the age you were born? There are lots of reasons why people sometimes don't get tall, right? A lot of it could be, oh, my mother, my father, my grandmother, we are all short, but there could also be like huge environmental influences. I say that because I got my adult height at about 19, 20 years. Those that were with me in high school know me as a very short fellow. And those that found me after university found a completely different person. And I suspect it was due to nutrition. But I was just lucky to get the right nutrition before my bones could no longer grow. But anyway, this newspaper article, based on another article, says that according to the survey, the average Kenyan man has lost a few centimeters of their height from 1962. The average height of Kenyan men in 1962 was 172.2 centimeters, 5 feet, 6 inches, and that has stagnated now to 169 centimeters, 5 feet, 5 inches. We have lost an inch of our height over that period of time. We blame bad governance, right? Now, there are scientists that have warned that this change in height that can be attributed to malnutrition and environmental factors has adverse effects on health, particularly that of mothers and children. And we know that taller people, on average, tend to have higher education, earnings, and possibly even social position. Is that true? You don't think so? I mean, you could do a little experiment here. We know your height and your current earnings. And test it. Yeah? Yeah. Let's do that later in the day. Let's see whether that's true. But be truthful about everything, right? Be truthful about your height and be truthful about your earnings. But I thought we should take this information out of this newspaper and see whether we can learn about distribution. So if you open up your R, you could actually simulate this data. Would you like to do that for me? Can you simulate this issue of men in 1962 being 172.2 centimeters, and in 2016 being 169? Can you simulate data of 1,000 men of that characteristic? You can? Okay, go for it. What would be the way to do it? Say that again. You have to assume a distribution. Okay, explain. I need to give you a mic.
I can speak louder.
Go for it.
Yeah, we assume that these are from a normal distribution with a mean of, for 1962, we have a mean of 172.2 8.2 centimeters. That's about 5 feet and 6 inches.
Mm-hmm.
And then, given that it's a normal distribution, we assume the variance is constant for this population. And then for 2016, the mean is 169.6 centimeters. So we will be having two distributions here. Not distributions, but two populations for
Two
2016
populations.
and for 1962, where the mean is different. Yeah.
Fantastic. So I actually did that for you. So you could get your laptop and get your R out, do your R scripts, and make a copy of this and see whether you can develop that population of 1972. Go for it. So here you are saying we are assuming a normal distribution of the heights, and the heights are continuous probability distribution that is symmetric, like Cosmas mentioned, around the mean, median, and the mode. We want to simulate some data from a normal distribution for the 1962 heights of men, of Kenyan men. The reason you are using this set seed, have you come across that in the lectures yet? Yeah? If you want to have it repeatable, you do need to have that code. So here we are assuming that we want to generate 10,000 random numbers for heights of Kenya men that has an average of 172. You want that from a normal distribution, and you assume, say, a 25 centimeter standard deviation. So you create an object called main height, whatever you call it. I've called mine main height underscore 1962. I want to follow Cosmas's advice. It's a normal distribution, so I use that function to say generate for me 10,000 random numbers that will have a mean of 172.2 and a standard deviation of 25, and then plot for me that data. So let's do that. Are you able to see from wherever you are, or should I make it larger? So I'm trying to do to Okay, there you go. You able to see it now? Much larger than this, huh? Okay, are you done? Okay. So when you observe the distribution of, oh, go up. This is day 5, so it's chap. Eh? When you're typing, be careful with your words. Art does not forgive. What if we change the standardization to something else? What should we say? How about standardization? So what happens when you change the standard deviation? What happens? If you change the standard deviation, say from 25 to 0.1. Hmm? Anyone? the thing I wanted you to see is if you change, say, the standard deviation here 25, which is what I gave you before, if you look at my graphic here, I am moving between 100 and 250, meaning that we have some men who are up to 2.5 meters and others who are just about less than a meter, right? And if you say there is not that much variation between persons, which you represent by, say, 0.1 here, what do you see? Now, almost everyone is between 170 to 172. Now, you sort of have to, I hope you sort of capture that information in your mind, that if you're doing like regressions, the one thing you really want out of your data is variation. Like if there's no variation between men and women, then there is nothing like gender, you know, as an influence to anything. So when you look at the outcome of interests, the first thing you want to establish is its distribution and identify whether there is actually enough variation. If you end up taking data and everybody was recorded as, you know, above 5 meters or above 1.5 meters, then there is nothing that you can model right there, because then the outcome is not varied. Yeah. Okay, so then you could go to, now we had 1962 men. We also have information about 2016. So right there. So in this case, we want to simulate some data, again from a normal distribution with a mean of 172.2 and a standard deviation of, say, 35 centimeters of height of men in 1962 and the changes that have occurred in the current 2016 era, where the average height is 169.6. Again, I've given a standard deviation of about 40 centimeters there. So essentially here we are creating two populations. The first population is what you've just completed creating, and then you have a second population that has these characteristics as mentioned. So could you create the second population with that? What I have done here now is gone ahead and provided the parameters for the population. So we now have an object called mean 1962, which is 172.2. Standard deviation of 1962 I've given you is 35. And the sample size I want to simulate is 10,000. Then set the parameters for 2016, which I have done right there. Set a seed, and then give me a simulated heights of men in 1962 and heights of men in 2016 using that. So you know R as an object-oriented programming, you can define things and name them, and you can call that name into your next code. Is that confusing you, or it's good? So let me walk you through that in a short. Okay, so here. So previously, we were just doing this and putting the 10,000 here and defining the mean and then giving the standard deviation to generate that simulated data. In this case, it's the same thing, just that I have named these things before. So I know the mean of 1962 is what was described, the standard deviation is that, 1962 population is 10,000. Do the same, and now you can call these objects into your function. Okay? So I want you to create those two objects, height 1962 and height 2016. You can call them whatever you want to call them, that simulate data of 1962 heights and 2016 heights. If you'd like me to come to your desk, just lift your hand and I'll come. All good? So those that are finished, you can go ahead and plot that data for 1962 and 2016 on one graph and show me a vertical line of the mean. Okay? So once you have got that data, I'm going to give you another code now that sort of tries to put the two data sets together. So if you wanted to make a comparison between 2016 and 1962 heights of men by plotting the data, what I want you to get is this graphic here that shows the height distribution of men in 1962 versus 2016. And the blue color here represents the distribution, which is behind, of men in 1962. And this orange color here represents the distribution of the heights of men in 2016. Now there are two lines here. One line is the line of 1962, and you see it's a little bit ahead of the orange one. And here, what is showing you is exactly what was described in that newspaper article. That if you look at the population of men in 1962 and the population of men in 2016, the average height of men in 2016 is shorter compared to, but this is a normal distribution. Then you might ask yourself, what is responsible for this observed pattern in data? Now, to answer that question, it's a regression, right? You do need to have a hypothesis that says, I think the reason that men are shorter these days is 24 years of one president. Then you can look at whether can that explain as a variable. Or you could think it's related to food security index. So if there's a way that we capture availability of food in a country over time, can we say that food security was better in 62 or worse? Or you could say it's the number of infections. Like we have less infections now, or you have more infections. Or you could say it's the type of food we eat. So all those are potential explanatory variables, because if we, or economists said, the taller you are as a nation, the better, you earn better, you have better GDP, then our job as epidemiologists is to try and improve the heights of the population. So you need to identify what are those variables responsible for better heights. And then we use them to continuously or incrementally improve the population's height. Together up to that point? So I realize it's going to take a bit of time to graph this, so you're going to get the notes and you can play with them, so as at least you get to the exercise that I want us to do today. So let's have a quick dummy example here. So assume babies at weaning age have an average of 6.3 kilograms. I hope I'm not too far away from the truth. What's the average weight of a baby at weaning? Yeah? Fathers? Absolutely no idea. You might think it's 15 kgs. Eh? But it's so let's assume the average weight of a baby at the time they stop suckling is 6.3 kilograms. Now, after that, you're giving them water, milk, and other things. They gain, on average, 0.1 kilograms per day for the first 100 days post-weaning. That's plausible? It's plausible, right? It's not a tricky question. Yeah, it's plausible. Okay. Now, due to various factors, these factors could be the parental genes, it could be socioeconomic factors, what they get to eat at the dinner table, or the kind of housing environment they have got, the amount of disease that they get exposed to, could affect a lot of things, but one of which would be weight gain. So given the different factors that affect weight gain, we can assume that the growth of children in that first 100 days post-weaning differs. And that variation out of all those different factors, let's give it, say, 2 standard deviations. Okay? So, again, we could simulate some data here. And the data is, the first information you need is the weaning weight. We're saying at the time of weaning, a child has 6.3 kilograms. We want to observe their growth for the next 100 days. So you're creating a sequence of 0 to 100 days. Now, in each of those days, there's a gain of 0.1 kilograms, right? So if we were to make an estimate of the weight of a baby in 100 days, what would we do with that information? High school now, right? Yeah? If on a daily basis I earn 0.1 kgs, how many kgs do you expect me to have earned at the end of 100 days? And if 10. And if I am 6 kgs, so what will be my kgs? 16, right? So you could say the weight of the child is given by their starting weight, which is the weaning weight, plus the number of days you're observing them, which is 100, multiplied by the weight gain, daily weight gain, yeah? And then, because you want to represent a data set that recognizes that there are variation in growth, you need to define that variation in growth, right? So that variation is defined by this thing here, exactly as we were doing before. We say that variation assumes normal distribution. We want to do it for 100 days, which is the observation time. And in each of those, the mean of that variation will be 0, but the standard deviation is 2. Okay? So then you can create a data frame that produces that data. So I would say you want to do that right now. Like, can you recreate that information given to you on the code? I hope you understand what you're trying to do, right? Okay, go for it. Just write that. will show better. Okay, so right there, I think, yeah. Done? Those that have gotten to the baby weight data, you can plot and let's see how the data looks like. So I'm going to run that. We can plot the data. So the next thing I want to do is plot the baby weight data, which is the data frame that you have created. And plot takes two arguments. The first argument is your x, what you want on the x-axis, and the second argument is what you want on the y-axis. In this case, we want to see how does weight on your y-axis change over time on your x-axis. That's why you're plotting the baby weight $day, which says get me the column called day in your data frame. So if you look at, let's see. So when you look at your baby weight data, if you have gotten to the level of getting the data frame, baby weight data has two columns, has a column called day and has a column called weight. Now, on day 0, the weight here is 6.8. On day 1, 8.3, like that for different children. Yeah? So if then you plot that information, we are saying we want the baby weight data. That's your data frame. Select for me the column day. That column day is going to be your x-axis in the plot. And comma, the data frame again. And then select for me column weight. That is your second column, and that will be your y-axis. Plot takes x, comma, y. So if I plot that, so if I just take that bit and plot, run that, then I see something of that sort. So I have got baby weight on the x-axis, and number of days on the x-axis, and weight on the y-axis. So play with that. The other lines here are just lines to make the graphic look better. So we are saying we want dots. We want them in color blue. We want them in a size 16. The type of line we want. And then label the x-axis with days of life post-weaning, and label the y-axis with weight into brackets kgs, weight in kgs, and title the graphic as baby weight gain over 100 days post-weaning. I should put post-weaning here. That would describe the plot pretty well. So the real plotting is only the first line. Everything else is about aesthetics. I think you'll only be lucky to do this if you have got your data frame. So yeah, so that's the last line of what you're doing before. So once you run this, I think you get this nice kind of graphic here. What would you observe? What would be your statement of data that looks like this? What's your interpretation of this? How do you interpret this graphic? What's the relationship? Huh? This is age, yeah? Yeah. The only difference is that you guys define this from the beginning, right? You define the baby starting weight, you define the age, like how long you want to observe, and you also define like how quickly they grow per day, right? So it's all your data. Sometimes you have an epidemiological study that gives you data like that, so you sort of are going backwards to find those parameters that define this pattern. Here you started with the parameters, you're showing the pattern. So the next important thing would be to add a regression line that tells you about the relationship in a much easier way. You can tell from the eye that there's a change in X is associated with a change in Y, right? Now we want to estimate what's that size of, that size of effect, what's the relationship per se. So again, from a plotting point of view, you could, I've seen you guys use ggplot, so I'm providing you an alternative way to plot it and include a regression line. So you could try that and see what you get. If you allow me, I'll explain the code very briefly. So I'm using a function called ggplot, which you have come across before. I want the data that you formed in a data frame called baby weight data that has how many columns? 2. One column is day and the other one is weight. So the aesthetics of it, which is given by AES, I want the x-axis to be represented by the column named day and the y-axis to be represented by the column named weight. Okay? Now, where that information meets, I want a dot, right? So put for me a geom point and color that point blue, and I want its size to be 2, it can be 4, it can be 5, depending on how you want it to appear on your graphic. This is the language of graphics. Like you can control every small bit of your graphic. And then comes your regression, the topic of the day. I want you to look at all those different method of linear regression and color that line red, and don't give me the standard errors around it. That's I've said standard error false. And then I want that line to be a size 1, and then label the axis. So for the title of the graphic, call it baby weight gain over 100 days. The x-axis call it days of life post-weaning, and the y-axis call it weight in kgs. And then the theme minimal means don't give me too much colors. I just want to see white and black, like for the main frame. So this takes a function that says I want a graphic that looks like this. You can remove it if you want, or you can keep it. So that's what that code is supposed to do. Run it and let's see what you get. Okay? Are we good? So you should expect to get a graphic like the one below. Okay. So once you do it, I think you'll end up with a graphic that looks like this, that tells us that there's a relationship between post-weaning days and weight in kilograms. And that line of best fit, that fits the data, you know, the method of least squares. So what you're trying to do is look at all these lines around and let the line run where you reduce the sum of squares of these errors, of these differences to the minimum. And that becomes your line of best fit. But essentially what you're looking for as an epidemiologist here, you want to know the slope, you want to know the rate of change that compares what you have got on your x-axis and the y-axis. So if I go back to this here, from a dummy example, so you end up with data sets that look like that's the distribution on your plane, and you have created your line of best fit. Now, a regression analysis can use that same data to see whether you can get back close to what the same parameters that you had used to generate the data. And so, in the running of the model, so let me just go back to a point here. If you look at the definition of how you are creating the weights, we say you have the winning weight. This is your starting weight. You're adding number of days times, and then some error, right? That forms your regression equation, because it often has an intercept, and the intercept here is your starting winning weight. Then you have something you want to estimate. The thing you're interested in estimating is this daily gain for every day of life post-winning. And then some error term. So what you see in those big annotations, it's basically trying to describe that. So in statistical modeling for regression, what you're getting is, so let's use this example right here, using that same dummy data. So we are creating an object, which is a regression object called baby weight LM, whatever name you give it Friday. We say it's a linear regression looking at the relationship between the weight of a child and the number of days post-winning. And I want to use the data that we created called baby weight data. That baby weight data has two columns. It has a column of day and a column of weight. So you want to see what's the relationship between the weight of the baby and the number of days post-winning. So once you run that model, this becomes an object. You can get a summary of that object, baby weight LM. Now the summary is presented this way from your R. So once you run it, you get this. And so what you observe out of that, there's quite some information out of it. There's an intercept, and there is a day, and there's an estimate for a coefficient here. At the end of that little graphic is a p-value, probability, given right here. In R, if you have this like three, what are they called, asterisks, it shows that variable is significant, statistically significant. So it's already giving you the answer right there. So it makes an estimate here that from that data you have given it, the starting point, or the intercept, is about 6.9 kilograms. What was our starting point? 6.3, not too far, right? And for every day you increase day times, the gain here is 0.08. What was 0.1. Again, not too different, because now this is an estimate out of your regression model. Okay? So if you were to interpret this regression model, you say, is day associated with a change in weight? The answer is yes, it's significant. What's the estimate of the slope? It says for every single day post-weaning, the baby is gaining about 0.08 as estimated by the model. Okay? Then there are other little information that you get out of it, like the multiple R squared, adjusted R squared. And this, the very basic interpretation of it is that the up to 60% variation of what you observe can be explained by the day, like the number of days post. So in our model, you're not explaining 100%. But we can say up to 60% of the variation can be explained by that one factor. Okay? Now we have used, like, you generated the data, you plotted the data, you developed a regression line, and you even calculated what is the estimate. Given that kind of data, what's the estimate of the relationship between weight and number of days post-weaning? Any questions so far? So does that run in your computer? So I give you 3 minutes to make sure you run and see whether you can get that result. I think one question that most people have asked is, you're getting slightly different figures for this, which is purely okay, because the data that we are using was generated by your machine. So you did a random generation, and the numbers your machine generated, the numbers mine generated, are different. That's why, like, I was setting the seed here, so as whenever I generate it, I generate the same number. When you set your seed, the same, you generate the same number. Otherwise, you expect every computer to have a different value, because it's not a data set I gave you, it's a data set you simulated out of your own computer. Okay? All right. I think I must leave you now to, let me give you some more information slightly, and then we can give you an exercise. Okay, so there are other motivating examples. I'll give you the notes to be able to follow. The more critical one I wanted you to do is, in statistical modeling in R, we assume in this lecture that you have some kind of fair knowledge behind linear and logistic regressions, and that's why, like, we dived right in and made you start working on it. But the point you wanted to stress is that the language of instruction that you're using here, R, is at home in statistical modeling. It's both easy to fit the model, as you have done with the dummy data that we generated, and even came up with estimates of the coefficients and whether they are important factors. And we can look at not just one factor, we can look at multiple factors. Right now, we are only looking at days, right? But it could be days and food. It could be days and mother's age. It could be days and mother's age and mother's education. You could have multiple potential explanatory variables in it. As you have seen, the simple linear model like we are using makes an assumption of, this is what you're trying to observe, the weights. This is the data that you will have. And then you have got an intercept, which is your winning weights, right? And then you're saying, we are estimating this beta 1, which is your average daily weight gain, which you'd already defined, but you can estimate given data for every day of change. And you can do it with another variable. So it could be, like I was saying, mother's education or mother's height. Again, you make an estimate of the contribution of mother's height to the weight of the baby, and then the error term. So that's what sort of explains that formula that you use there. So then the idea of a regression is to make the estimates of this beta, like the average daily weight gain per day, or per mother's level of education, or per mother's age, or per 1 kg of meat eaten. Those are the estimates you're making. And then we test in the statistic whether that would come out of chance or that is possibly as explained by that factor. So the idea for your regressions is always you have got this variable of interest, which is your response variable. It's the outcome you collect from your epidemiological studies. And then there are all these plausible factors that you have been discussing the whole week that you do want to see their association with your response variable. So the syntax for doing it, right now you are just doing plus, right? I think they are, let me show you so as it's just clear. So you named your model whatever you named it. I think you call it baby weight LM. You could call it whatever you call it. You have a response variable as explained by your predictors. Our predictor here was days. Yeah? And our response was? So if you have more than one factor, in R what you're doing is I want the factor of days plus the factor of mother's age plus the factor of household income plus whatever other factor that you have got. And then these parameters, you can even play with them. If you wanted the square root of a figure here, maybe the square root of income, you just add that square 2. Or if you're interested in getting an interaction between mother's age and mother's education, then you'd use a multiplication. And if you do that, the way that would be treated, so if you say you have an interaction term, let's assume that we hypothesize that a mother's economic status is associated with a mother's education status. And we think those two interact. So you could actually have, I want to see an interaction between the mother, the age, the mother's variable, and the interaction between the two of them. So you'd sort of put X and then put the dots X2. That would be treated by R as an interaction. Now if you write something of this sort, of three factors you're looking into and you're putting those big multiplication signs, then this is interpreted as, I want the main effect of X1, main effect of X2, main effect of X3, the effect of the interaction between X1 and X2, and the effect of interaction between X1 and X3, and the effect of interaction between X2 and X3. Make sense? Yeah? That's a really good question. So what would be a confounder? Give me an example.
Maybe husband's employment status, yeah?
So if you thought husband employment status is an important potential confounder, then you include it as one of your, you could have it as plus X3. So just include it in your model. Okay? Do you understand this bit here? About interactions?
That one would be like looking at the how the three together combined
Yes.
are related to the outcome.
Yes, so the interpretation would be, I want to know the value or the coefficient associated with X1, with X2, and X3 as a factor. And in addition to it, I want to test whether there is actually an interaction between X1 and X2, X2 and X3, and X1 and X3. Okay? And then there could be a lot more that you could do with it. So one might say, my interest is to look at the impact of a factor above the mean, right? Say, we know the mean income of a household in Kenya is about? An average household in Kenya, we have about 10 million households in Kenya. What's the average income of an earning person in Kenya? 10K. How many people earn 100,000 and above in Kenya? Okay, so supposing your interest was to look at the impact of having above average income. In your analysis, you could say, I want the mean of the population, yeah, which is the mean of the income of the population, and I want to look at the value that the person has got, or the value that I've got in my model, above the income. So if you put this big, I don't know what's called, like a big I, capital I, it says, do for me this calculation, and the result of that is what you put in the model. Make sense? That I think would be possibly examples that you have to deal with when you give you exercises. So I've got some data sets that I would like you to work with. I think you only have like 15 minutes, so I'll complete the lecture and then give you an exercise, whichever you are able to work on, and then George Paul will decide how we move forward with that. So I'll move away from this and tell you, one of the data sets I've got for you is a data set of the first year of life of a little zebu cow. The East African shorthorn zebu. It's a little cow with a hump that lives often in the pastoralist and areas of Western Kenya. very hardy. It does not produce lots of milk, but does not die from disease. It has a balance. Uses its energy to survive rather than to give you milk, unlike the big Frisian animals that you keep. So, this data set is you recruit animals at birth, basically a week after they are born. You have an idea of what's their weight at the beginning. And then every 6 weeks, you observe and weigh them, so you sort of know what is their weight as they are gaining. And then you look for all infections that they are getting in their first year of life. So you have protozoan parasites, you'll have worms, you'll have virus infections, and you're observing every time what they're getting. Now, that data set means you can have information at the start of the study. You know what the animals are born with, and then what they get over time. So if you take one of the potential outcomes, like how we're discussing babies before, now we are looking at little calves growing. Yeah? Time for a dance. Little calves growing. You could look at what's their starting weight and how much weight do they gain over the 1 year. That's what this graphic is showing you. So it shows you an identified animal that has a code. So all these numbers, CA, represent a specific unique code for an individual in the study. Then what you've got on the x-axis is time. So you've got time ranging from 0 days, which is basically the first week of life, to 350 days, which means at the end of 1 year. Every small dot that is blue here represents a time you weighed the animal. And on the y-axis is the weight. It's written here as kilograms per day. So this is basically, I think that's miscoded, it's basically the weight of the animal at the time when it's weighed. So the example here is this calf 0028. At birth, it weighed just below 30 kilograms and never got weighed again because it died. Whereas this calf here, 062, got weighed at birth, and over time, it got to about 60 kilograms by the time it was 1 year old. What I'm hoping for you to see is a variation in the growth rates of these animals. So if the line is a little bit steep, it means that animal is really growing fast, and the ones that appear flat, that's a struggling one. Now, you could replace that outcome with anything. So you could say there is a good marker in a human being about their health, and that marker continues to increase, so you could look at the slope of the change of that marker. So the data set to give you has this information. It's for you to determine what are the main factors responsible for the observed variation in growth and the estimate. So there are two things you're getting out of that regression. The first is a factor associated with a positive or a negative growth? So does it reduce growth rates or does it increase growth rates? Is that factor significant? Like statistically, can you observe that without chance? Right? And then the second important question for your regression is the size of effect. Like you want to know what's the contribution of that one factor to the growth. Then you do your regression. Now in this case, it's a little bit tricky because you have got an individual that has been measured how many times? Like multiple times. It could be 5, 7, 8 different times. That means in your data set, you'll have an individual that is the same with multiple measurements. So if you're not careful, you could end up making this big statement about repeated measures, right? Like you can tell animals that die fast or quickly don't provide lots of measures Whereas those that live for the 1 year, there's a reason they live for 1 year. They're possibly already doing pretty good. So by not considering that some of these data sets are related to a single animal, and you should consider that, then you might end up with a wrong estimate of your regression coefficients. Make sense? The last bit I wanted to mention is that what you did is a nice example of getting a quick answer, but regressions have assumptions, right? Like you have to assume that, for instance, your outcome data is normally distributed. Now, before you jump to say, here is the result, you do need to test and do diagnostics of your model to say, does this model meet the assumptions that we put against like that kind of distribution work? So there are ways to do model diagnostics. So one of the questions like for linear regressions is, are residues normally distributed? Is there a relationship between the response and variables? Is that linear? Do we have outliers? So if you have in your data like errors or some, different kind of individuals, you could end up with a really big estimate of the factor, yet that's driven by outliers. So you need to know, are there outliers and what do you do with those outliers? And there are even tests to test that. So you have like a little graphic here that is not very visible. Let me see whether you can see it. Or for diagnostics that you have for R, again, I think I would let you read that yourselves to make sure that at least the assumptions that are important for linear regressions are met. I saw in our timetable today, I think we have multiple linear regressions, right? Yeah, as part of the practical. So discuss that, and I think that's what you're asking, like how do you control for potential confounders, or how do you determine like the impact of multiple things happening, like this multi-causal concept that you were discussing before. Put them in your model, the interpretation of which is you're holding almost everything else constant to say this is the impact of this one factor, but you have accounted for the others. If you take the example of the demographic health surveys that the country does, it has 180 different variables and more. You don't own a model that has got all those variables in. There's a way to minimize the number of variables that you have got in your model, and that's also like an area you need to study to know how, if I have got 100 variables, how do I arrive at the most parsimonious model has 5 or 6 or 7 variables. I don't know that we are covering that, George. You did yesterday. Fantastic. Great. So this is actually a repetition. And then, so far we have just discussed like the linear regression that assumes that the outcome has got a really defined normal distribution. But that's not true, as we saw at the beginning of the lecture. Sometimes you have got like yes, no outcomes, death, survival outcome, sick, not sick outcomes. That cannot be a normal distribution. So there's an extension of regressions that I call generalized linear models that takes that one outcome and tries to transform it in a way that you can model it. So one example is when you have 0 and 1 data sets, where there's an event that happened or did not happen, dead or alive, then you can transform that 0 to 1. I think, and I had George trying to explain that for logistic regression before, where you're looking at the probability of falling between 0 and 1. So what you end up with is a distribution that takes the shape of a logistic shape, right? Now, the way you make that decision is dependent on the distribution of your outcome. So should I carry out a linear regression? Now, if I've got height data that's nicely normally distributed, then a linear regression is right. Okay, what if I have data that has like that kind of nice shape, but has a long tail? So meaning that it has a diversion, diverse on one side, then what's the appropriate distribution to use? Then that you'd have to learn, yeah? Like the use of negative binomial distributions and the likes. Or if you have got the 0 and 1, then you make a choice between these binomial distributions. The beauty is like all these things have been sorted out for you. So you just sort of need to know the distribution to use, and then there will be a link, what kind of transformation that you require, and that function is already provided for you in many of the statistical packages, inclusive of the R that we have been describing here. So essentially, the components of this generalized linear model will be this random component that specifies whatever I was describing, the probability distribution of the dependent variable, whether it's normal, binomial, Poisson, and then you'll be able to even handle non-normal distributions. So to give an example, some of the link functions you've got in R, you've got like the logit one or binomial, the identity one, which is what you've been using now, which is linear regressions, gamma, and the likes. And again, all this is dependent on the outcome variable that you're dealing with and the way it's distributed in making your choice. So taking the example of a logistic regression, we can test the relationships between, say, the infection status of an individual and some blood picture, maybe the Paxel volume or PCV. And for that, then you're using the binomial family. So the same way you are doing the linear regression, when you come to do this generalized logistic regression equations, you sort of, all you're changing is, instead of LM, what you had before as for linear regression, you specify to the program that what I have is a GLM, a generalized linear model. Again, uses the same syntax. You say, this is the outcome variable of interest. In this case, it's an outcome variable that takes a 0 or 1. And then I would want that to be related to a variable like PCV or blood picture or whatever it is, or sex or gender or income. Then you can include that. So you're looking at the relationship between these 0 1s and a potential explanatory variable, which could be anything, biologically plausible, or that would make sense for you. And then you have to define the link function that you're using here. In this case, you're saying this is a 0 and 1 kind of data set, so I'm using binomial. And again, the interpretation of which is not too different what you get out of the logistic regression. You get some information about, is that factor statistically significant, so you still get your p-value right here. But then you have to do a little bit more because the result of that is like odds ratios. So, and I think that has also been talked to you a little bit. Okay, so as I end, I've only like in a very brief way described logistic and linear regressions, but there are lots other kinds of regressions that exist. So there could be ones that is based on count data. It could be one that's based on time to event. Or it could be one that's based on a hierarchical structure. By hierarchical structure, I mean like if I get multiple data sets from each of you, and then I put that into a data set, there will be data sets that are related to cost mass, 5 observations or 10 observations. Now, if I say also cost mass works in medical school, and there are people who work from the School of Social Sciences, and there are people who work from School of Education, that's also a different structure. There may be things about medical school and School of Education that are different. So in the context of doing a regression like that, you cannot ignore that fact. You cannot ignore that I have got multiple multiple observations from the same individual of a certain area or a certain characteristic. So when you account for that, then you're getting into what they're calling the multivariate regression that looks at data in a hierarchical structure. And there are many more, even up to the new things like we talk about machine learning and AI, that's still, parts of regression. You could think about regression for time series data, like the curve data that I was showing you. Sometimes you have got data that has got multiple zeros. So if lots of zeros, then the appropriate regression for that is not just your linear regression or your Poisson regression. There are specific regressions that deal with those kind of problems, like the zero-inflated regressions. So if there's anything that you take out of this lecture, is you should give careful consideration as to the type of distribution of your outcome data. Like, that's a starting point. Once you have got this variable of epidemiological data that comes to you, play with it. Make sure you are using the appropriate distribution for the analysis of the factors associated with that outcome factor. Okay. I think it's time. I have exercises here, so I'll hand them over to George and the team, and then maybe you can integrate them in the practical sessions that you have put in for today. But thank you. I'm happy to take any questions. If there's no question, happiness. Great. Okay.
When we were simulating data for the first for men in 1962, we set seed to 123, and then the second we set seed to 42. Set seed. Yeah, what does that mean? What does it replicate if we set it to 123 and then for the second time we are doing it to 42?
Seed is an integer vector containing the random number generator R, and instead for random number generation in R can be saved and restored, blah, blah. I don't know whether there is an issue about 42, 123, or 128. You know, George?
No, basically it's to allow everybody. So when you're doing a simulation, right? When you do a simulation, it produces different numbers based on the combination. So to make sure that all of us get the same results, we can set seed to 20 for all of us. Now, if 10 of us set seed to 20, 30 of us set seed to 50, others set to 123, those three different sets of people will get different numbers. Because it's a simulation. We're generating numbers randomly. When you do randomly, there's always a difference.
So the idea is you're telling the computer that from this point to this point, I want you to generate random numbers based on the seed. So you're taking 10, generate random 10. So that's why George is saying when you pick the numbers, the seed differently, then you're telling your computer, one is saying pick from 10, the other one is pick from 30, the other one is pick from 123, you get? But then the seed is basically you pull from where the randomization happens. So we're setting it at 10 so that we get the same randomization.
Actually, I'll confirm that. I think it's also, you get the same for the single computer. Like, even if you have the same seed for, you all get like kind of different random numbers. But if you repeat it on your computer, then you're still getting the same number. That's why you're getting, everybody was getting different kinds of estimates. Yeah. Okay. Any other? Yes. That's a good question, whether it's always you should run mud variable. Like in the cause and effect lecture, we talked about like the different contributors to the outcome. Now, by running just one variable, like that's a good starting point, but it doesn't tell you about potentially all the other important players into it. So if you think, for instance, the height of a child is determined by the genetics of the mother and also the nutrition of the mother and the nutrition of the child and the environment they are living in, then you do need to account for that. Otherwise, if you only have the genetics of the mother, then the estimate you're making for that does not account for these other potential contributors to it. So I think as a practice, I mean, you'd never publish like just data between an outcome and one explanatory variable, right?
Maybe my objective is just to identify like some of the contributors, like not necessarily getting a cumulative effect or adjusting. I just want to see, okay, age is associated with the outcome, gender.
Yeah.
And then someone else can carry on.
So again, if I take the example of Down syndrome and what were you looking at? And birth rank. Yeah, so if you sat and said, I found birth rank is associated, someone else should look at the other factors. Then maybe that's publishable, but not in a good journal. And here we are to do good science. So, yeah. Like the concept of effect, as mentioned earlier, is complex. Like it's not simplistic. You should do the best you can. Not too complicated, but the best you can to make sure that the estimates that you have got represent reality. Because models are basically a simplification of reality. Don't oversimplify it. Like, yeah, but also don't overcomplicate it. But I think like one single factor is a little bit too simplified. Okay. Back to you, Josh. Thank you.